All right, welcome. Today, we're not just going to talk about artificial intelligence, we're going to build it. Well, kinda. We're going to lay down the blueprint, the fundamental architecture for a digital brain. We're going to ask the big question, how do you even begin to structure a machine so that it can see and make sense of the world? So, where are we headed today? First, we'll tackle the massive challenge of mapping something as messy and human as our feelings. Then, we'll see how an AI is trained, kind of like an apprentice chef learning a new craft. From there, we'll dig into how machines understand language, what I like to call its social DNA. And then, the main event, we'll zoom right into the core building block, the digital neuron itself. Finally, we'll tie it all together to see why this blueprint really matters.
All right, Section 1, the map of feeling. Before a machine can even think about recognizing an emotion, we first have to define what an emotion is. And we have to do it in the only language a machine truly understands, math. This is all about translating that subjective human experience into objective, cold, hard data.
So this really brings us to the million-dollar question, right? How do you actually teach a machine to feel? And this isn't just a technical problem, it's almost a philosophical one. How do you build a bridge between the beautiful, chaotic reality of human emotion and the clean, binary logic of a computer?
Well, it turns out there are basically two ways to think about this. On one hand, you've got what we could call the Lego set approach. You treat emotions like separate blocks. Happiness is one piece, anger is another, sadness is over here in its own little box. They're distinct categories. But honestly, that's a bit too simple, isn't it? That's why the rainbow model is so much more powerful. It sees emotion as a spectrum, a fluid continuum where feelings blend together, like feeling both joyful and sad at the same time. That nuance is absolutely key.
Okay, so the gold standard for this rainbow idea is something called the VAD model. This is it. This is the mathematical bridge we need. It basically plots any emotion you can think of on a 3D map using 3 axes. You've got valence. That's just a fancy word for the pleasure scale, from really good to really bad. Then there's arousal. Think of it as the intensity or energy level, from super calm to totally wired. And finally, dominance, which is all about how in control you feel. Those 3 things together can pinpoint almost any feeling.
And here's where it gets really cool. Look at this. An abstract feeling like joy gets translated into these precise coordinates. A machine sees it as 0.81 valence, 0.51 arousal, and 0.46 dominance. Now compare that to fear. It's got a negative valence, super high arousal, and negative dominance, you see? Both are high energy, but they're on totally opposite ends of the pleasure and control map. For a machine, these aren't just random numbers. They're like GPS coordinates for our feelings.
Okay, Section 2, training the apprentice chef. So we've got the map. Now, how do we teach the machine to actually read it? To make this crystal clear, we're going to use a little metaphor.
Now, this is super, super important. Modern machine learning isn't about writing a bazillion if-then rules. We don't sit there and code, if the corners of the mouth turn up, then label it happy. No way, that's old school, and it just breaks. Instead, it's about giving the machine a whole bunch of data and letting it discover the patterns for itself. It's just like an apprentice chef, learning to cook by feel and experience, not by following a super strict recipe book line by line.
And this whole learning journey really has 2 main parts. First up is the training phase. This is where our apprentice, the AI, studies thousands, maybe millions of labeled examples. Think of them as recipes that already have a picture of the finished dish. It's learning to spot the key ingredients, or in our world, the key features. Then you have the prediction phase. Now our chef is all trained up. We give them a new mystery ingredient, and based on everything they've learned, they have to make a guess. Aha, I think this is a happy face.
All right, Section 3, the social DNA of words. We've talked about the process, but what about the ingredients themselves? I mean, how do you even begin to feed something as messy and abstract as human language to a machine?
The magic here is a technique called word embeddings. See, for an AI, the meaning of a word isn't in some dictionary, not at all. Its meaning comes from where it sits in relation to all the other words in a huge mathematical space. Words that are close together are related. It's like a giant social network for concepts, and this network is literally the social DNA that an AI uses to understand language. Let's make this a little more concrete. Here, concepts like queen or prince are broken down into numbers or vectors based on different qualities like royalty or youth. So a queen would score high on royalty and femininity, a prince high on royalty and youth. The machine doesn't feel what a queen is, but it knows her exact mathematical address, and with that address, it can do some pretty incredible things.
And this
This is where it gets mind-blowing. You can actually do math with these concepts. If you take the vector for king, you subtract the vector for man, and then you add the vector for woman, where do you end up? Exactly at the vector for queen. This is what people call identity math, and it's how an AI starts to grasp the complex relationships that define our world.
Okay, deep breath. We've gone from the 30,000-foot view of mapping emotions all the way down to the nitty-gritty of words. Now it's time to go microscopic. This is the climax of our journey today. Let's pull back the curtain on the blueprint of a single digital neuron.
Okay, take a good look at this, because this is the heart of it all. AI is really an act of biomimicry, and this table shows you exactly how. On one side, you have a real biological neuron. On the other, its digital twin. Let's walk through it. Your neuron's dendrites, they're like little antennas that catch signals. For the AI, those are just the inputs, the raw data. Now, how strong are those signals? In the brain, that's controlled by neurotransmitters. The AI's version is weights. We'll talk a lot more about those in a sec. A real neuron has a threshold. A signal has to be strong enough to matter. The AI has a bias, which is kind of like its starting mood. The cell body in the brain adds up all the signals. The AI does the same thing with simple math called summation. And finally, if the total signal is strong enough, the neuron fires. That's the action potential. In the AI, that final fire or don't fire decision is made by the activation function. You see? Every single piece has a direct mathematical counterpart.
All right, let's zoom in on what might be the most important part of this whole thing, the weights. The best way to think of a weight is as an attention knob. Every single piece of information, every input, has a weight attached to it. That number tells the neuron how important that signal is. It's how it decides how much to listen. If the network starts to learn that, say, the crinkling around the eyes is a huge tell for a real smile, it's going to crank the weight for that input way, way up. If some other piece of data is just noise, it'll turn that weight way down. This is it. This is how the network learns what to pay attention to.
Okay, and the last piece of the puzzle for our neuron is the activation function. I love this analogy. Think of it as a grumpy bouncer at a club. So all the inputs get added up, and that final number gets shown to the bouncer. The bouncer's job is simple. Is this signal a big deal? Should I let it pass on to the next neuron? Yes or no? But it also does something else that is absolutely critical. It takes that final number, which could be massive, and it squishes it into a predictable, manageable range, usually between 0 and 1. Why? To keep the whole system from going haywire. Without this bouncer, the numbers could just explode and crash everything. So the bouncer keeps things stable and makes sure only the important stuff gets through.
So there we have it. We've built a single digital neuron from scratch. Now let's zoom back out and see how this tiny little engine connects back to our grand mission, building a machine that can actually understand the world around it.
And this really gets to the so what of everything we've talked about. A machine's perception is only ever as good as the features it learns to look for. Think about it this way. If an AI is only trained to look at the shape of a mouth to see if someone is smiling, it's going to be fooled all the time. It won't know the difference between a real, genuine smile and a fake, polite one. Why? Because it's missing the most important clues. It's missing the true story being told by the eyes. The real difference between a shallow guess and deep understanding is all about teaching our apprentice what features really matter. That's the whole game. So let's just take a moment and look at what we've actually built today. We started by mapping human emotion onto a 3D grid. We laid out the process for training our apprentice chef to spot patterns. We figured out how to decode the social DNA of words. And then we drilled all the way down to the blueprint of a single digital neuron. The whole structure is here. We have the static blueprint of a digital brain.
But that raises a pretty massive question, doesn't it? We've built the structure, the car is assembled in the garage, but we haven't turned the key. The whole thing is just static. It can't do anything until it learns from experience. So how does this machine actually learn from its mistakes? How does it tweak all those millions of attention knobs on its own to get smarter and smarter? Well, that dynamic process of learning, that's exactly what we're going to break down next time. Thanks for following along.